probably close to 35 minutes. Okay, welcome back. Luckily for you guys, all right, Brett came in this morning and had a great idea that we might start out a little slower coming back from the week. But he's got some really good information for you here to present to you about some opportunities, okay? Both on the CET and MET side, okay? So don't be afraid, okay? This is construction-oriented opportunity here, but either one, valuable stuff to look at. So with that, I'll give it to Brett Martin. He is an instructor here in the Civil Engineering Department, okay? He teaches a lot of the heavy construction, soils. Some of you might already be in some of his classes right now. He said he thought he'd recognized a couple of you. Poor people that have to go to his class right after this. Right?
Well, good morning. The 8 o'clock class on a Monday after spring break. Look at you guys. You're actually here. You guys are going to pass this class. Hey, where's my CETs? Show of hands. Okay, cool. And where's my METs? All right, awesome. Hey guys, what I'm going to present to you guys today real quick is the ECIV 492 professional elective class. If you're a CET, you're required to either take this class or the internship during the summer, okay? You got to take one or the other, or you can take both. And so where my METs, again, you guys can take this class as a professional elective. So what is ECIV 492? It's what we call the Reno competition class. And what we do is we prepare you guys as a team of 6 to how to bid and estimate a project. I.e., you're actually going to learn how to build stuff, okay? And then we will take the team down to Reno, Nevada, and compete against all the other schools on the West Coast, essentially. And we just came back almost a month ago from Reno, Nevada, and it was a good time. We did well. We got second place in mixed use, and so we took 4 teams this time around. And we take everybody that joins up and goes through the class. So why would you want to take this? If you have any interest in construction whatsoever, this is probably going to be the best course that you can take for the program. A lot of METs, you guys are going to go straight into construction too, typically about a third of you. So if you're interested at all, this is the course to take because it actually wraps and rolls everything up into it. And then where's my guys that have taken it already? Okay, we got a couple guys in here that have already taken it. Talk with them about what it is and what it can do for you. And if you're seriously looking for a job, it's a great way to get an internship and a job. If you take the class, you have to put it on your resume because that's going to get your foot in the door for an interview. So if you are interested at all in taking this, please raise your hand and we'll hand out a flyer to you guys, which is basically this. We're going to do a much larger info session this Thursday in 108 Barnard, and we'll start at about 4:30 in the afternoon. It's all on the flyer, so if you're interested, please raise your hand to grab one of these guys to talk about it. And
I'll also get this out on D2L as an announcement, so in case you don't get one today or want to look at this.
So, is there any questions about what this course is? I can answer a few things right now, but we can answer a lot more on Thursday afternoon. Yes, sir.
I'm just going to raise my hand for us.
Oh, you just want the flyer. Okay, all right. So, and actually, we got a couple of guys that are in here. Did you guys want to talk about your experience with the Reno competition? Either of you guys?
Sure. Yeah. I mean, it was first off just the connections you make. You do get in front of a bunch of. We have some workshops throughout the year that get you in front of employers, and just from those employers, you start to build a rapport. And I had a couple internship offers just from that. Let alone the massive job fair they have down there. I mean, companies across the U.S. that want to talk to MSU alumni, and the competition is huge. I mean, you get to present in front of a company on stuff that you'll actually do in real life and deliver on bids and proposals and RFPs and that kind of stuff. That was something I've never been a part of yet. Got a bunch of that experience under my belt. I feel like going into my first job, having this class is the experience. I already know kind of what they're doing and what they want from you, and so it helped out a lot. Best class to take at MSU if you're going to end up in the construction industry for sure.
Yeah, I mean, post after your presentation is done, you walk out of that room and you've got like 5, 6 employers standing either side, outside of that room, looking to hire you, get interviews for internships, full-time jobs. So, you know, if you're looking for a job, looking for an internship, this is the way to get it.
Questions, comments? Yes, sir.
I had a class that starts at 4:30 on Thursday.
You just come by with my office and talk to me more about it one-on-one. That's fine. Yeah, we just can't pick a time that everybody's off, and nobody wants to stick around after like 6 o'clock anyway. So again, METs, you guys can't take that. We had an ME take it this year, so and it counts as a professional elective. So we'll probably see you guys in a few other classes a little bit later on. Thank you guys very much. Appreciate your time.
Thanks, guys.
Thanks, guys.
And back to the regularly scheduled.
Yeah. Now for the exciting shit.
I'll steal it. You
Yeah,
want that
take-
flyer?
I'll keep this one, and then I'll.
You got a couple of those.
Yep. This is my pile.
Oh, okay.
This is my pile, Brett.
Thank you.
Yeah. Thank you, man. Appreciate it. All right. As Brett said, that is an amazing class, okay? Especially if you're going into construction. It really gives you some hands-on experience doing bidding and estimating and putting a whole project budget together, and that's what you compete against other teams on, is pulling together a project estimate and a budget for a real project. So they come up and they tell you, this is our project. Maybe you're building a dam or you're building a road, okay, or you're building a commercial building. You got to go through and dissect that project and divide it up into all of the little palatable pieces that you would in the real world, and actually go out and put numbers to it and like bid it, right? And then you have to have this full package that then you present to a panel, right, on your project, and you get graded on that, okay? So, and that's what contractors do in the real world, right? In order to get a project, they competitively bid for it. And so that class is hugely beneficial to give you some of that real world experience, okay? Now this class is also hugely beneficial, right? Right? Excitement? No? Yes? So before we left for spring break, and you guys forgot everything that we talked about for the first 7 weeks of this class, okay? We were talking about stress transformations, right? Stress transformations is the principle or the concept with which when we start getting more complex loading, right? We have shear, we have normal stress, okay? We have shear from, say, torsion, we have normal stress from, say, axial loads, and then eventually we're gonna get bending involved, right? So when we start getting all of these additional load sources that pile onto an element, in this case, we had this solid shaft, okay? It had an axial load and a torsion on it, right? It's going to create shear stresses and normal stresses, right, on an element that might be oriented like so. And figuring those stresses out is fairly straightforward, right? It's pretty easy. Everything is oriented nicely, perpendicular face to our applied normal force, okay? We can figure out our shear stresses due to our applied torque, okay? But because of the application of multiple load sources, right, axial load and torsion, we end up getting this change of internal stresses if we looked at planes that were oriented not just perpendicular, right? So we figured out what the stress state was on this block that's oriented kind of along the axis of our shaft, right? But if we start looking at, we start cutting this thing at different angles, we've decided that if we looked at Moore's circle, we end up getting a variation in stress at different angles or orientations of that block, right? And that's important because we could have an orientation that's not such, that's nice and clean and neat and oriented with respect to the applied forces, right? We could have an orientation or a cut of this material that material is experiencing a lot different stresses, right? In this case, if we were to rotate our block, right, these 2 points were our original block orientation. And if we were to rotate at that angle alpha, which is twice that of the real rotation, right? The rotation on Moore's circle is twice that of the real world. So if we were to rotate that down, we can find locations where we get our principal stresses, right? Our principal stresses, sigma 1 and sigma 2, those are our maximum and minimum stresses, right? Or, in this case, we could rotate, say, counterclockwise a certain amount, and we would find our points where we would have our maximum shear stresses, right? Tau on the top and bottom of our circle, which we would never find if all we did when we analyzed this as a designer or a manufacturer, right? If we just looked at the stresses at H, okay, those would not capture either of the maximum normal stresses, right? Sigma 1 and sigma 2, or the maximum shear stresses, right? And when we're relating our maximum demands to our allowable capacities, we would miss the mark completely on this, right? We would be relating the wrong stresses. If we related the stresses that we found at point H, the stresses on this block, and we related those back to, say, the material that we had, maybe it was steel or aluminum, bronze, or something like that, right? We would be comparing the wrong things. We would need to be comparing, right, sigma 1 and sigma 2, right? And tau max, right, or maximum shear stress, to make sure that the demands are less than the capacity, or demands are less than the allowable capacities of our materials. Right? All of that come back really quickly, right? Got it? Been thinking about it all spring break, right? Dreaming about principal stresses and maximum shear stresses, right? Okay, good. So, let's see, where are we at? In this example problem, we're going to go through a number of more examples here. Okay, we wanted to illustrate Moore's circle and determine the principal stresses and the max shear stress, right? And so we went through and we figured out the stresses on a known stress block that's oriented as shown, right? We know that there were no normal stresses on the top surface of this H. There's nothing running around the perimeter of the shaft. Okay. We have this P force, this axial force that's a tension, so outward normal force, which is an outward normal stress. We figured out sigma x, well, it's just force over the area. That's our P over A. We did that up here, right? Up here, P over A. We got 95.5 megapascals. Then we could figure out our shear stress. That was due to our applied torque, right? Based on the direction of our applied torque, we realized that our shear stress, right, on the right-hand face of this is going to be acting downward because our torque is rotating counterclockwise. So we were able to then figure out that that arrow on the right-hand side is downward. If that one's downward, we can figure out all the other three stress directions, right? So we figured out our stress block. From there, right, our stress block that we determine is really just coordinates for us on the Moore's circle, right? We have our coordinate of our normal stress and shear stress on both the x face and the y face. And so what did we do? Well, we just plotted those 2 points on a coordinate system established based on Moore's circle principles, right? Where our x-axis, remember, is our normal stress axis. Our y-axis is our shear stress axis. Positive shear stress is downward. We have this counterclockwise rotation, right? Curling our fingers, our thumb is pointing out of the page. Up above, it's clockwise, thumb's going in or negative. Our normal stress, positive on the right-hand side, that's tension, right? Negative on the left-hand side is compression. And we plot our 2 known points based on point H, right? So we plotted our x normal stress and our tau xy. So that's our coordinates, 95.5 and our 63.7. And then similarly, we plot our y face. We got 0 and then 63.7. Knowing that, right, our y coordinate is going to be equal and opposite on either side of our x-axis. It's always going to be the case, right? So we plot our points. Because we can plot our points, we can find a center. We can find a center. We can find a radius. We found those. We can then draw ourselves a nice circle. And that circle represents all of the possible combinations of normal stress and shear stress at any given plane in our shaft, right? If we were to cut this shaft, right, we started here, If we started to, say, cut it at 2 degrees to the right, 3 degrees, 4 degrees, 5 degrees, all the way down until we got to 90 degrees, we would essentially figure out all the points on this circle, right? Because if we took our stress on our X face, right, and we started cutting it, you know, at a counterclockwise rotation, 1 degree, 2 degree, all the way around to 180 degrees, well, that's 90 degrees in the real world, right? So we just went from cutting it vertically to cutting it horizontally, right? And so we would figure out all the possible stress states. Well, why the hell is that important? Well, one, we want to capture what's the maximum stress for the material. But two, there's always a possibility that we're not going to have an infinitely long piece of material that we can always utilize, right? A shaft on, say, we had our example for a large boat, right? A container ship, for instance. You think they just make one long shaft for the propeller? No, they can't do that, right? They've got to then splice it together, right? It comes in multiple pieces. There's issues with both on the manufacturing side, you can only make a shaft that's so long. But two, the biggest thing is you can't transport things that are super long either, right? We're pretty limited. Railroad is probably the biggest help for transportation, okay? But you're still limited in the radius of curves. They got to make through tunnels, stuff like that. You might be able to get away with, say, something that's 60 to 80 feet long on a train, okay? If it's going on a truck, if it's going down the interstate, most tractor trailers are, say, like 53 feet long. You might be able to get some longer ones. I don't know if you guys have seen like wind turbine blades, right? 150 feet long, stuff like that. Gets very, very expensive, very, very specialized, okay? So if you needed something that's longer than that, you're gonna have to splice it together. Well, this is when Moore's circle steps in and says, okay, if we splice it together, and say we wanna splice it with a butt joint, right? We just cut that shaft and we put the two together and we say weld it together or glue it together, right? What are those stresses? Well, sometimes it might make more sense to actually bevel that shaft at a certain angle and connect that shaft at an angle, because given the applied loads, right? We know that if at a rotation here, we figured out what that alpha was, right? Rotating to our principal stresses. In the real world, it was 26.4 degrees clockwise, right? Rotated clockwise. So if we took and cut a plane at 26 degrees, right, clockwise, that means we're going to have a huge tension stress, right? We're going to have this sigma 1, that's going to be our greatest normal stress. We're going to have a big tension stress acting on that face, right? We won't have a shear stress, so if we connected an element at that angle, that specific angle on this shaft, right? We wouldn't have to worry about shear stresses, but all we would have to worry about is a big tension stress, right? If we cut it perpendicular to that and we wanted to cut it like this, right? So this was 90 degrees. Well, now if we looked at 90 degrees to that, well, that's going to be the other end of our circle, 180 degrees. That's going to be sigma 2. Well, we know sigma 2 is actually negative, so it's in compression, right? So if we were to splice that shaft, we cut that shaft at that line right there, right? We put two shafts together. Those two shafts are really going to want to stay together, right? They're going to be in compression. And so you can decide on what type of glue you use. Maybe the glue you use is really good for tension and not very good for shear. Well, you can cut this shaft at a given plane where it doesn't even have to handle any shear stress, right? So it becomes very important to understand what are the mechanics, right? What's going on at a given plane in our material, so we know that the material is accurate or adequate, but also the connection of pieces are adequate as well, okay? So that's the power of doing this. So they asked us for what's the principal stresses. Well, we have sigma 1 and sigma 2. We calculated that. That's just our center coordinate, right? Plus the radius, or the center coordinate minus the radius. And then from there, they asked us, right, as part of that, our principal stresses are at a given orientation. So we calculated based on the inverse tangent, right, of that little triangle here. We're trying to rotate down to the x-axis In order to do that, we figured out that alpha was 52.8 degrees, which yielded a real world rotation of 26.4. And then finally, they asked us, what's the maximum shear stress? Well, that's just the magnitude, right, of our radius. That's the top and the bottom of our circle, okay? Well, our maximum shear stress is really just the radius. Just like that, right? Acting both in a clockwise sense and a counterclockwise sense, depending on which face you're on. Right? Any questions? Yes, no? All right, we're gonna go through a few more. Keep this before we lose it. Well, as I mentioned, eventually we're gonna get to bending, right? Bending's our last load source. We're gonna get to that here in the next few weeks. We have to, right? Semester's coming to an end, all right? So in this case, we have a pipe that's mounted vertically. Say it's a flagpole or something, right? On this flagpole, it's got an axial force acting down of 17 kilonewtons. It's got a horizontal or a lateral force acting at the top of 3.2 kilonewtons, and it's got a torque acting on it of 3.75 kilonewton meters. Well, all of those load sources end up creating, really? Huh, interesting. Anyway, sorry. All of these load sources end up creating stresses, right? So we have an axial force of 17 kilonewtons. Well, if we divided that by the area of this pipe, we would get 8.31 megapascals, okay? So we have a axial contribution of stress, right? Eventually we're gonna be looking at this point H and what's going on at point H. So we need to know our axial stress. Well, we'll eventually figure out bending. But if we were to look at bending at point H, well, that has to do with, well, what is our lateral force times its moment arm? So we took the 3.2 kilonewtons, multiplied it by 0.8 meters. That gives us our moment at point H. We get 2.56 kilonewton meters, right? We get a bending contribution. Then finally, we have a torque contribution, right? And as you can see from this, we're spinning clockwise. The stress produced is clockwise around this pipe, okay? Minimum at the inner diameter, maximum at the outer diameter, right? 35.897 megapascals, okay? So we end up getting a stress block if we looked at H. Well, we'd have a axial contribution. We'd have to add a bending contribution. And then finally, we would look at a torsion contribution, right? Our shear stress. So we do very similar to what we did in the last example. We would end, right, with this stress at a known orientation, right? We know this orientation because it's looking at point H. It's oriented with the axis of our pipe. Right? So we get our normal stresses and our shear stresses at our block. And really what I wanted to gather from this is saying, okay, now that we know our stresses, let's find the maximum principal stresses given that element, okay? What would we do from here? Gave you a nice big review. You've been stewing over old spring break. I'm going to give you an opportunity here to walk me through this. First step, if I want to know the maximum stresses, right, or our principal stresses on this flagpole, right, flagpole or whatever it ends up being, okay, it's got some applied loads on it. I figure out a known stress state and a known orientation. So I gave you this, okay, you know this. What would you do to figure out your principal stress? What's the first step? This is a safe place, man. I'm telling you right now, safe. Okay? Not a wrong answer. Give me something.
More circle.
Moore's circle. Did I hear Moore's circle? Okay. Everyone agreeing? Moore's circle? Anyone say that shouldn't be the first thing we do? No? Okay, good. Moore's circle, right? So in order to plot Moore's circle, we need coordinates, right? We need axes. So I'm going to draw in some axes. We know we have a y-axis. We know it's positive downward. We're going to have a x-axis, positive to the right, okay? Below the x-axis, is that a shear stress that's clockwise or counterclockwise? Counterclockwise, right? Right-hand rule, thumb sticking out of the page is positive. So I'm going to say that anything that we plot down here is going to be a shear stress that's rotating my block counterclockwise. Anything above, I'm going to say is clockwise, right? Opposite. So I'm going to plot normal stress on the x-axis, shear stress on the y-axis. Okay. Well, looking at our stress block here, right, we have coordinates for it. The coordinates for this block matches, right, the coordinates on our flagpole, right? We've got x pointing off to the right. We've got z pointing 90 degrees to that. Y is along the axis. So if we pull out this little h cube, right, or h block, we're going to get coordinates that look like that, right? X on our side faces, y on our top and bottom faces. So with that being the case, what's sigma x? Zero, right? So if we were to plot this block on this Moore's circle and we started with the x face, what would be the coordinates that we would plot? Zero. What's the next coordinate? Zero.
35.89.
Yeah, 35, right? We want the shear stress. Nope, you're getting ahead of yourself. You're starting with the y, right? So if we start with x, you're right, 0. Then we want the shear stress. That's our y coordinate, right? Our shear stress is rotating our block clockwise, right? So it's going to be above the x-axis or on the negative side. So we're going to be 0, comma 35.9, right? What's the next point we're going to plot? 57, 35, and what's the y coordinate? Right, that's going to be our x and y coordinate of the y face. A little confusing there, right? We're looking at the y face. We have two coordinates on this face, right? One coordinate is going to be the 57.36. What's the other coordinate? Or 35.8, right? Or 35.9. Now it's going to be on the opposite side of our x-axis. It's positive because that is rotating our block counterclockwise. So now we're down here. So if we're 8 above, we're going to be 8 below. And I'm going to say we're down here. So this is negative 57.36, comma 35.9, right? Should be negative because it's a compression stress, right? It's acting towards the face. So we've got our 2 points. This is when I get to show off and do this. Something beautiful just like that, right? So now we have our 2 points. Draw a line between them where they intersect the x-axis. That's our center, right? And we could just scribe a circle based on that center. And we have now plotted every possible stress combinations within that flagpole, right? Given those demands at that location, right? If we were to look at point H, right, and we moved it at the very bottom, what would change? Any ideas? The bending changes, right? Which we haven't really talked about yet, but that's the big component here. Axial force, that's not going to change. If you cut it here, you're still going to have that axial force. Torque, if you cut it here, you're still going to have the torque. There's no torque getting pulled out of this shaft anywhere else except for at the base, right? So it's important when we start considering, especially with bending, that we are looking at a discrete point in this flagpole, right? So we've got our Moore's circle. We've got a center. We can calculate our center. It's our average stress, which is sigma x plus sigma y over 2 equals negative 28.7 megapascals. Radius, well, it's square root of sum of the squares, right? We're just essentially figuring out what our, well, I guess black, oh, I want something different. Right, we have our x and y. We're going to figure out the hypotenuse. We're going to square root the sum of the squares. So I'm going to say that this is equal to sigma x minus the center stress, which we just calculated. I'm going to square that, plus I'm going to take tau xy, square that. We're going to get a radius equal to 46 megapascals. Right. Once we know the radius, we know our maximum shear stress, right? And more importantly, it's the maximum in-plane shear stress, which we'll talk about in a second. But we're going to have the maximum shear stress on our XY plane, right? Those are our points at the top and bottom of this circle. Tau max, we're going to call this in-plane maximum shear stress, which we've been dealing with to date. We're going to talk, there's a difference between in-plane and absolute. Well, now that we know the radius, we know the center, we can figure out, well, what is sigma 1? Sigma 2, right? Our principal stresses, our maximum and minimum normal stresses. So we got sigma max equals sigma 1 equals the center plus the radius, 17.3 megapascals. Center minus the radius, right? Now we're going to start at the center, working our way to the left. Well, that's negative 74.7 megapascals. As part of this, though, we always want to calculate what's the orientation of these principal stresses, right? What angle would we need to slice our flagpole in order to show our maximum normal stresses or minimum normal stresses? Well, in this case, if we rotated alpha, right? If we went clockwise, right? This was our X face. This was our Y face. We rotate clockwise, so we take this element, right? And we rotate it some amount. We're not going to call it alpha, we're going to call it theta, right? The actual rotation in the real world. So if we rotate alpha on Moore's circle, how far do we rotate with respect to theta? What's the relationship between alpha and theta? 2 times, right? So alpha is twice that of theta. Well, if we figure out alpha, we can just use the inverse tangent relationship, right? Which is the inverse tangent of the opposite over adjacent. Well, again, opposite over adjacent, right? Our y coordinate over our x coordinate. So we get tangent -1, 35.9. It's our y coordinate, 28.7. That's our x coordinate. We get 51.4 degrees, right? Alpha is 2 times theta. So alpha over 2 gives us theta, which is 25.7 degrees. Right? So if we wanted to look at an actual stress block, right, depict this, similar to how we just depicted point H there, right, with a block, we would just rotate a block kind of, sort of, H. We need to rotate it 25.7 degrees, right? Rotate it downward. And we know that if we rotated it downward now, our x face is going to be sigma 1, or our maximum stress. Our maximum stress is positive. Is that tension or compression? Tension, right? So our x face is in tension, so we're going to get some stress arrows that do something like this. I'm going to say this is sigma 1. That's 17.3 megapascals. Well, sigma 2 is negative. That means it's in compression, right? 74.7 megapascals in compression, right? So if we went back to that flagpole, and right at point H, we were to cut at 25.7 degrees, right? On that face, we would have this big compression force, right? And similarly, if we were to, this one's going to be really shallow, but if we were to cut at a plane that was perpendicular to that, now we're going to look at the y face, or sorry, the x face, right? If we cut it at 25.7 degrees, we're going to see this big compression force, right? 74.7. Well, if we would have to cut it at 90 degrees to that in order to start seeing this tension force. So that's what we would see if we cut that flagpole perpendicular to that. So we had a big compression force. In this direction, we're going to have some tension force, right? So that flagpole is essentially undergoing a big tension stress along this plane right at point H, and it's undergoing a big compression force along at point H at that orientation. Does that make sense? Okay, kind of heavy. All right. Well, something we need to think about, and I tried to find something, I couldn't find anything to really help depict this. But as I mentioned in this example, right, when we calculate tau max is the top and bottom of our circle, right? It's the maximum magnitude that we have on our y-axis, which is our shear stress. Right? That's tau max. Tau max, though, right, on this Moore's circle is relating to the xy plane. It's in plane maximum shear stress, and the plane over which you're getting the maximum shear stress is the XY plane, right? We have XY coordinates on that block. Because in the real world, we have 3 dimensions, right? And when we started this whole process, we talked about the fact that we're going to assume plane stress. And what plane stress is just saying that we have 0 stress in the out of plane direction, right? If we looked at this flagpole, for instance, right? There's no stress pointing outside of H, right? It's not coming out of the page, it's 0. Okay? There's nothing trying to squeeze this pipe through the thickness, okay? And so we assumed a plane stress case, and in engineering, or structural engineering, mechanical engineering, okay, a lot of what we deal with, we can make that assumption that we have plane stress, okay? It simplifies a lot of things, okay? Usually we start looking at things in plane, all right? Because that third plane, the z-axis, or out of that pipe, we assume that the stress is 0, right? You can't have any stress acting out here. It's just in the atmosphere, right? Well, that still has a coordinate on Moore's circle, right? If the normal stress is 0, which we'd had, right? Sigma x, the normal stress was 0, right? There was no stress acting around the perimeter of our pipe, okay? And it has a coordinate on Moore's circle. So what does that mean? Well, if we start looking at the max in plane versus the absolute shear stress, well, now we have to start incorporating that third dimension, right? So now instead of just looking at the XY plane, now we're going to look at the XZ plane and the YZ plane. Because even though we're assuming plane stress, right, where we have 0 shear stress and 0 normal stress on that face, okay, it still has a coordinate on the Moore's circle, right? It's a point on Moore's circle. It's the origin, okay, 0, 0. So if we look at in plane, shear stress, that's the maximum shear stress on our considered plane. And in our case, when we look at plane stress, we assume that z coordinate, the stresses are 0. Right? So we're always really looking at the xy plane. And so all the Moore's circles that we've drawn to date just relate that x face and the y face, right? We get the coordinates off our block that we establish. We have an x face coordinates of the normal stress and the shear stress, y face coordinates, normal stress, shear stress. Okay, so we have a stress block that ends up looking like something like this. Right, we get a stress block that looks like this, and these are our coordinates, right? This is what we've plotted on Moore's circle to date. We have sigma x, right, and tau xy, right? Shear stress on the x face in the y direction, that's what these two stresses are, right? Talked about that, how the sign convention works in the nomenclature on shear stress. Y face, very similar, right? We have sigma y, normal stress on the y face, and then we have tau yx, shear stress on the y face in the x direction, okay? So we've established our blocks. And the maximum shear stress is the maximum stress on our Moore's circle that we plot based on these two coordinates, right? We get a circle for that. Well, when we look at absolute, we need to look at the maximum shear stress on all planes. Now we need to go back. We need to start considering that z plane, right? That z coordinate. Now when we draw our stress block, right? When we consider, let's go back here. Consider our block looks something like that. We're going to have sigma x. We're going to have sigma x over here. We're going to have our shear stresses. And we have these coordinates, right? Oh, this is tau xy, tau yx, right? We have these, same as what I just drew up here, we're looking at again. Well, now, instead of ignoring the third dimension, we need to start looking at it, right? We have this z dimension, which is really out of the page, right? Out of the plane of this block, this square. And if we look out of the block, we know when we have plane stress, what do all of those stresses equal? Plane stress, right? We've assumed that to date. That's just like the flagpole. We're talking about the stress that's out of the thickness of our pipe. What do we assume that equals? 0, right? So all of those things are 0. I tried to get, like, the best thing last semester I had was just a cardboard box that was a nice cube shape, okay? So now instead of slicing, well, this is a nice cube, okay? So this is our cube, right? Now it's 3 dimensions. We've been playing with plane stress. So if we looked at that stress block, right? We've got X running that way, Y running straight up, Z running out towards you guys, right? And so to date, we've just been looking at a slice of this box, right? And we just look at a slice of it. So you're essentially looking at it from your side. We've got this nice, just flat surface. We have 0 stress, right, acting towards you, okay? We have 0 shear stress acting on these faces also, okay? Well, the Mohr circle we've been drawing to date is the Mohr circle associated with just the stresses on the X face and the Y face, right? Well, now we need to start slicing this in the other directions, right? So we're going to slice it this way, okay? And then we're going to slice it this way. And when we slice it this way, now we're going to have the X face and the Z face. When we slice it this way, we're going to have the Z face and the Y face, right? So we're going to have 3 more squares that we need to consider, right? So we've considered this one already. We consider it when we look at in plane. Now we're going to have 2 more, right? And those coordinates of those 2 blocks are going to now be X and Z and Y and Z. So if we looked at, that was terrible. So if we look at 2 more blocks, well, now we're going to have sigma Y, Y, and we're going to be looking at a block with the coordinates of Y and Z, right? That's essentially cutting this block towards you and away from you, right? So now we're going to have the Z axis, or the Y axis pointing upward, and the Z axis pointing towards you. So now we're just looking at a sliver of that block cut vertically. And then similarly, we're going to do the exact same in the ZX direction, right? And those are our stress blocks. We have no shear stress, right? Because we know on the Z face, on both of these, on the Z face, our shear stress is 0. If the shear stress is 0 on one face, it's got to be 0 on all 4 faces, right? We know that from equilibrium. So those all go to 0. We know the normal stress is 0, right, on the Z face. And we're going to have some sort of normal stress on the X face, or we could have some on the Y face. Okay, we'll finish this concept on Wednesday. No homework yet. My plan is to assign some homework on Wednesday. It'll be due next week, okay? And you'll have a quiz next week. Got to lead you into this slowly. I know this week is going to hurt. Okay. Don't forget Reno. I'll try and get